So this is for process dynamics and control. This is homework 2 part B. So what we're going to be doing today is we're going to be using homework 1 part C, and we're going to use the conditions for that, and we're going to pair it with part A of homework 2 as well. And we're going to be using this for a tubular reactor of the same volume, except this time we're going to be dividing it into 200 perfectly mixed sections rather than 100 like we did in part A. And we're going to simulate slight backmixing. And to accelerate the numerical simulation, we're going to implement code with Google JAX AI framework. So I have part of that set up here, which I'll explain later. And we're going to create a plot of concentration and temperature profiles through the tubular reaction over 2 seconds and qualitatively explain the results. So just to start, I've already gone ahead and put our library filled with NumPy and SciPy stuff and all. And then our first part of the JAX function is this print options, and it's just going to help with I guess printing our options when we are done with the code. So that should be done. And then I have our variables and all put in here for the sake of time. I don't think it'd be a very good video if I'm putting a billion variables in there. So we're just going to go ahead and start and define our right hand side. We're going to use t and vector as usual. So first we're going to go ahead and define our CT, and it's going to be np.split. Use vector and 2. Next we're going to go ahead and define our change in concentration, which we're going to use as np.zeros, and if you remember, that's what we used in part A as well. And we're going to do the same thing for the temperature. And next, what we're going to do, since we have a multi-component system, we're going to use our Arrhenius equation. I hope I spelled that right. And we're going to use k equals k naught times np dot exp to make this a exponent, and it's going to be negative er divided by t, and I believe we have er and t already, so this just gives us our value. And then we're going to go ahead and define our mass balances, which is going to be dc, and we're going to use that first value in our array, and it's going to be q times cin minus c, again that first value, that data set, divided by v, and we're going to subtract that by our k at the first value times our c at the first value. And then we're going to do the same thing, except this time it's going to be for all other values in that data set except for this first one. So I'm actually just going to go ahead and copy this to make it easier. Except here, what we're going to do is we're going to skip our first value and go to 1. And then for this, we're going to use all of our values from 1 just from here. And then for the k, we're going to do the same thing. And then for c, we're going to do the same thing. And it's just saying that we're going to skip this 0th value, and we're going to use 1 over. And we're going to do that for both of these. So this is our mass balance, and we've set that up. Okay, so now we're going to go ahead and do our energy balances to account for our dt. So we're going to do basically the same thing. And that sound, my computer's getting a little loud. So we're going to do pretty much what we did before, just slightly different. So this time we're going to count for our T in minus our T, I guess initial value you could say, and divided by volume minus our overall heat transfer coefficient times our the initial minus our TC value, and this is going to be divided by rho times V, or volume, times concentration, and then this is going to be added with our negative enthalpy, and it's going to be multiplied by C0 times our K 0. I think this is supposed to be actually minus. I'm going to go ahead and actually copy and paste, because we're also going to be doing it for all the other values in that array, so we don't need to do anything there. So we're going to have -1 as before. This is going to be 1. Do the same thing right here. And then for our concentration and our K value as well. Yep, I think everything looks good there. And then we're going to go ahead and return with np.r underscore r dc dt. And there we go. I think that should work. Oh no, I'm going to have to run all. Alright, there we go. And then I'm just going to go ahead and run that again. And then we'll go on to the next. So now I changed a few things. This was a subtraction, where actually it's supposed to be addition, and this is supposed to be divided by rho times C, and we do the same thing right here. Okay, and there we go, that part is done. Now we're gonna utilize that JAX feature that we are supposed to use in this. So something that I learned is that the code is pretty much the exact same, except for the fact that we're going to be using a little bit of a different structure. So instead of the np.split, we're going to do jnp dot split check 2, and then for our DC, we're going to have jnp dot zeros at n, and then same with our dt, and yep, and then for our radius equation, we're going to do the exact same thing, except this time we're going to have jnp.exp negative er divided by t, and then for mass balances, we have a slightly different structure, but dc dot at 0, and then we're doing underscore set. Oh, no, sorry, it's supposed to be dot set. There we go. And we're just going to go ahead and copy our equation down. It's supposed to be the exact same, just in between. There we go. And then our DC once again, DC dot at set. Do the same thing and just copy it over. And same for our energy balances. So we're going to have our dt function and then dt dot at 0 dot set. Oops. Go ahead and copy this very long equation. Just put it in there, and then we will have that for our 1 over there we go. So that's our Arrhenius, or not Arrhenius, our Jax functions complete, and then we're going to go ahead and return with gnp.r underscore dc dt. There we go. That's the Jax function. So we're going to go ahead. Oh, there we go. So before we get into the parameters part of this, there's 2 more lines of code that we do have to add. So I'll go ahead and write it out. So this jax.jit function, or I guess feature, is going to be added to the code, and it stands for just in time. And according to Copilot and my understanding, it basically allows Jax to compile it into highly optimized machine code, which is using accelerated linear algebra before running it. And I believe that basically just means that it allows for more accurate representation of our code and the data that it's compiling. So that's what that does. And then we also want to plug in one more thing. So RHS, right hand side underscore Jax underscore Jack, and gonna have our Jax dot jit, and then our Jax dot Jacobian feature, and then score Jax and 1. Yep, I don't think we have to put dot jit right there, but dot jack, but this is our second line of code, and then we're gonna go ahead and run it, see if it works. Yep. And now we're gonna get into our parameters. So like last time, we're gonna do our n times, which equals 100 this time, and then we're gonna get our t plot. So now we're going to get to our dt, which is 10 divided by our n times. That gives our change in time. And then we're going to have our t plot, which is our np dot line space as usual, and then 0, our 10, which is 2 seconds that we're doing for this simulation. And then we'll have n times. And we'll go ahead and do our res, which is sp.integrate.solve underscore IVP, and kind of got it right, but we'll have our Jax function, and then have our 0 to tendency, and then our np dot r underscore our initial concentration and our initial temperature, and then we'll have our method, which is as usual redow, and then our dense underscore output, which is always true, or at least in our case it's always true. And then we'll also have our jack function, which is RHS underscore jacks underscore jack. And then we'll also have to add our concentration profiles, which this is just res dot sol tplot, and see if it works. And yes. So now we're going to go ahead and make our concentration and temperature profiles, or our plots that we need. So we're going to start with C plot and T plot representing our concentration and temperature, which this will just equal our NP dot split, and we're going to have res dot sol for T plot for time, and then we're going to have two values, and our axis will start at 0. So yep, that works. And then that concludes for our more of the calculation side of things. And then we obviously have to make our plots. So we're going to make our subplots. Spell it right. Yep. And then we're going to have rows equal 1, columns equal 2. And then we're going to set our t index, our loop, in range of n times. And then we're going to make, as per usual, our fig.add underscore scatter with our x, which equals np dot arrange in terms of n. Yep, it's not double R. So, and then our y, which we will set as our C plot, and we're going to make it into a matrix including our index. And then we're going to have our row equal 1, column equal 1, and then we're going to have our name, which is going to be a little bit of a weirder than usual type of thing, and kind of got it, but it's in T plot, we're doing dt times T index, and we need a bracket right there, and we use these curvy brackets. If we didn't, it turns into a I guess, let me just show, it turns into more of like a it's not like a line of code really. It's like you're just saying, it's like it'd be the same thing if you were going to be like, oh, say hi. So there's that, and then we're going to have our legend group, which equals t underscore index, and that is that for our C plot. And then we'll have our temperature plot as well. So we'll, did it correctly. So we have our np.arrange as n, and then our T plot, and it's going to be the same thing as the C plot basically, except the only difference on this part is it's going to be in column 2. And then we're not going to have the name for it. We're just going to have legend group equals t underscore index, and then show legend as false. And there we go, and then we're almost done. So we'll have fig.show, and okay. Unsupported format string passed to list dot format. So let's have that figure out the error. Might take a second. Or maybe we don't need the. Oh, yeah, I think it just didn't need the brackets there. And let's go ahead and just run all, just in case. Yep. So that's our plots, and yep, it looks correct. Now, so what do these charts actually mean? So we have our x-axis showing that it went through 200 cycles, and we have like 100 or so, I guess, data points. And we can see that there's a little bit of an inverse relation between the concentration and temperature. This is an exothermic reaction, and basically what we're seeing here is our concentration went down, meaning the reaction is at like its, I guess, maximum reactivity, or I guess that's how I would say it. And temperature spikes up at that same time. That like at 20, it goes up, and as we can see, it kind of dims out throughout the tube when the reaction starts picking up a little bit. Um, and this could be a little bit dangerous as well, depending on the chemical, I guess. Especially when it gets this high, it could cause explosions or something, flammability. But it seems like that temperature shot up, and then it's just calming down as the reaction picks up.